Hello and welcome to another podcast. Continuing on alkane reactions, want to get into more specifically certain types of reactions in terms of Markovnikov addition and predictability. And so I'm also going to go to something called oxymercuration. Before getting there, though, I want to talk about why we care about like which carbon it adds to. And so SN1 reaction, we had rearrangements. That's possible anytime you have a carbocation. And so in alkene chemistry, because H plus goes on as the first electrophile to add to an alkene, because that happens quite often, rearrangement is quite an issue actually. And so I want to just look at why compound rearrange and then revisit the stability, the relative stability of carbocations and add a few pieces to it. So first off, this double bond can act as a nucleophile. When it does, it can attack the H, forming a new bond between the terminal carbon and the H and leaving a plus charge in its wake where the electrons swung away from. The Cl is also going to get those electrons and finishes an anion in this case. So I'm going to get rid of my arrows and hope the ones that come in are prettier. They come in. I've drawn as two possibilities, and really it isn't two, it's just one. It's the same compound, but I just want to do two things with it. So again, it goes and it grabs that H. So I should specify that the H in question is on the terminal end. So it's here and here. Carbocation is here on the more substituted carbon. And for this structure, I drew the H that we don't consider in this bond line drawing. I want to emphasize because it's going to become kind of important in this picture. It could be in front, it could be in back. That's actually not all that terribly relevant because it's free to rotate and it's not a chiral center. But I want to draw it in front just for ease of drawing the next step. So here, I'm going to ignore any possible rearrangement and see what happens. So the secondary carbocation can then have the chlorine come in and attack, and it goes on the second carbon. So if I call this carbon 1 and this carbon 2, based on double bond, then that would be 1 and that would be 2. And it would go right where expected. But as mentioned with SN1, rearrangement is very quick. It's easier to move within the same structure faster than it is to move through a solution to get to that structure. It's easier to change seats on your living room couch than it is to run across the entire campus and end up, let's say, at a different chair in a totally different building. It's just easier within the same region. So this pair of electrons are free to move over to this plus charge, and with it, bring the H. So again, we call this a hydride shift because when it moves over, the hydrogen is negative. It's taking the electrons with it, the bonding electrons. So you can think of it like an H minus moving over. So when an H minus moves over, it will leave a plus charge in its wake. So again, these electrons will just simply move over like that. And so now I've ignored the H, but it's on this carbon. There's a second H that's already there, or first H, I should say, there, and this is the second one on. So it's not a chiral center, so I'm once again ignoring it. But now we have a case where it's carbon 1 and 3. Carbons 1 and 3 that'll be involved in this reaction. So now the chlorine can come in and attack there, and you end up with the chlorine 1 away from where it was before. So this hydride shift resulted in a different product. Because this is the more stable carbocation, tertiary, this is your major product, and you will get a minor amount of this one where it goes through a secondary carbocation. And I won't put percentages up because, as we'll come to learn, different temperatures allow for different distributions of product. So without knowing a specific temperature, I'm simply going to say major, the majority, this minor amount, this one might be like 95 to 5, 98 to 2, could be 60 to 40. I don't care as long as I know this one's the higher percentage. So carbocation stability that we've learned to this point, we've learned that tertiary is better than secondary because the more R groups, the more alkyl groups that can donate to stabilize the carbon with the plus charge, the better. So tertiary is more stable in secondary, secondary more stable in primary, primary more stable in methyl. So much so that tertiary can exist, secondary we can get them, primary really, really hard to get them, and methyl are essentially non-existent. Okay, but there's a second group of carbocations I want to include And that is the ones that are driven or stabilized by resonance. And so if you have any sort of resonance with respect to the alkyl group or the carbocation next to on an alkyl group, if it's next to a double bond, it can be stabilized. So groups that can stabilize it, an allylic or allyl cation is one where the double bond is right next to the plus charge, and so it can resonate over, and in doing so, share the plus charge. So that makes it a little more stable. Resonance always beats inductive effect. You can have the same thing with benzyl. You have a benzylic carbocation where that comes over, for instance. And so we end up with certain double bonds still in place. So I have that one. And I have a plus charge here. And these double bonds stay in place. And then it can further resonate. So it can move around and so forth. And then you also have next to something with a lone pair. So it could be a nitrogen, could be an oxygen, just some heteroatom where that lone pair can donate in. And in doing so, offers some resonance stability. Now you put a plus charge in an O or an N or whatever heteroatom happens to be an example we use. And it's not ideal, but it still offers some stability to the carbocation. So because resonance beats inductive effect, the resonance stabilized carbocations are going to be a little bit better than tertiary. Now within that, we have to realize this is a primary allyl stabilized. So secondary allyl stabilized would be better, tertiary allyl stabilized would be the most stable of all of the resonance, or of all the possible allyl resonance ones we have. So I still want to consider primary, secondary, tertiary here, but I also want to add in the extra resonance. So the more stable the carbocation, the more quickly it's going to move to that structure, and the greater percentage, the more molecules that'll pass through that intermediate. Okay. So because of this rearrangement, it can sort of mess up certain reactions where we add acid first. So you add an acid, hoping to add, let's say, H plus and some electrophile, some of the group across the double bond. Because of rearrangement, it may not go where you want. So we carry out certain reactions that are designed to avoid rearrangement. So that this way, we get the OH exactly where we want it. One of these is known as oxymercuration. So we have oxygen attached to an acyl group bound to a mercury. So mercury is going to behave very similar to basically a proton. If it loses one of the OACs, one of the OAcyl groups, then it becomes He plus with only one group attached, and that's like a really bulky hydrogen. So we'll talk about that in a second. But because just like H plus, it's the first thing to go on, it chooses the more available, the more open spot, the less crowded. So note that it went on first and added here, and then OH in the form of water that gets deprotonated defaults into the other carbon. This reducing agent, sodium borohydride, we're going to talk a lot over the course of the remaining course of this semester. But for now, simply note that it delivers an H minus, which can help stabilize and push electrons back to mercury. Okay, interested in the basic mechanism. So the fundamental mechanism, the first part of a reagent, the first substituent, the first group, atom, whatever it is in that particular case to go on, will always choose the better seat, the less crowded seat. So because mercury is first on, and notice it's now HgOAc1 with a plus charge instead of OAc2, it's neutral. So an OAc minus is left, leaves this as a plus. This will go out and get that plus by attacking mercury. So it bonds mercury, that leaves a plus charge on the neighboring tertiary carbon that water will attack. So the first group on, in this case HgOAc plus, chooses the less crowded carbon. OH, in the form of water, will go on the more crowded, and then you reduce it down. So one of the things going to transition into is looking at mechanisms. And whenever we do a mechanism, we have to ask two questions. Question about the regioselectivity. Where does the reaction occur? So our answer is HgOAc goes on first, so it goes the less crowded carbon. OH defaults to the more crowded carbon. So it's Markovnikov addition. And then stereochemistry, we don't get any new stereocenters. So in this specific case, it doesn't matter, but we always have to consider that. So this one, no big deal. So mechanistically, I'm going to worry about where it goes on first. So Ag coordinates in this case, the more crowded. So what we mean by that is, although it adds less crowded, it can share electron density with the more crowded one. And because it stabilizes that carbocation, there's no need for rearrangement. And then BH minus simply attacks, delivers an H minus to the carbon, and then removes the HgOAc plus. Okay, so let's look at the actual mechanism itself. So oxymercuration reaction, going to start with that same compound. So the same alkene. So it's 1, 2, 3, 4, 5 carbons long with methyl. So 2-methyl, 2-pentene. I don't name it E or Z because these substituents are perfectly equal, so can't really have a priority. It's going to come and attack, like we said, from the less hindered side. So this intermediate with a tertiary carbocation, but before any rearrangement could potentially occur, you can actually get some orientation of electron density to help stabilize that intermediate. So Hg, and I'm going to use the word back bonding. It's something that we see from metals. It's a term. It doesn't always fit and isn't the perfect term here, but still the same idea that because metals have so many electrons, they have such a large electron density and available electron density at that, because as a metal, they're not very electronegative, they share. It can share this electron density back. The dashed line represents a coordinated, not a full covalent bond. So it's lining up, so it takes the plus and reduces the partial plus, and the mercury shares part of the plus as well. So that full plus is now shared across 2 atoms and is coordinated, so there's no need for rearrangement. Then the water is free to attack. The water will come in and attack that carbon. Notice I have it coming in from the backside to break that bond. If there was a stereocenter here, we'd have to consider it. Because there's no stereocenter, I have no way to prove that it came in that way, so I'm not going to worry about it. But I know mechanistically, you break a bond by attacking from the backside. So the water goes on here, mercury is here. You can simply deprotonate. So when it gets deprotonated, it turns into the alcohol. So this is the first step. So I put an OH on the more substituted carbon. I have a mercury acetate, I guess, or acetyl mercury on this group. So not going to go into the mechanism yet. I will get into this, but long story short, H minus is what this provides. It's a hydride donor, can come in, deliver it to that carbon, kicks out the electrons back to the H, G, and that reagent is free to start the process over. pH 10, basic conditions help to deprotonate, to make sure, well, basically make sure we don't protonate our hydride. Okay, I hope this seems okay. So as we're going through this chapter, there's a large amount of information, just tons of information. So I introduced the concept of a spider chart for some of the more simplistic reactions. Ultimately, I'm going to ask you to make 2 spider charts for alkenes. One is going to be the basics where they kind of all look the same, a lot of halogens, a lot of OHs, a lot of Hs. We're going to make one that's a little more complex. I'm going to put this one on the more complex side because it forms that strange intermediate. But just know that this leads to a Markovnikov addition of an OH. I also want to once again emphasize, I arbitrarily put OH in back, of course in CH3 in front, but because it's not a chiral center, it can go either way. This doesn't specify this as like one of 2 enantiomer products. There's not a chiral center, so they can't be enantiomers. But if there was a chiral center at that point, then we'd have some in front, some in back. You'd have to account for both of these. So it's going to be a lot of really short stint videos where we do 1, maybe 2 reactions in a video. And we're going to keep on building on this spider chart. So it's going to be an awful lot of podcasts going on for this particular chapter. I hope this helps, and see you very, very soon at the next podcast. So done for the time being. Thanks. Bye.